A very good afternoon to one and all, and welcome to DDAG's Open House Edition 24. I am Ashu Mathur from DDAG, and today we have a very eminent hydro engineer of India and Bhutan, Shri R.N. Khazanchi Sahab, who will talk on tunneling in Himalayas, technological interventions at Tala project Bhutan. Now let me introduce him to all of you. Shri Rajendranath Khazanchi Sahab was born and brought up in Kashmiri Pandit family of Srinagar, J&K. He studied engineering at VJTI and secured an honors degree in civil engineering from University of Bombay in 1962. Same year, he topped the selection list of J&K Public Service Commission for appointment as an assistant engineer. While in J&K, he served various river valley projects in different capacities in all the three regions of Jammu, Kashmir and Ladakh. In 1981, government of Libya appointed him as chief project engineer of housing project of Al Khoms State. He joined NHPC in 1983 and worked in several capacities till 1997. For completion in project implementation of mega project like Salal in Jammu and Kashmir, Rangit in Sikkim, Tanakpur in Uttarakhand, Chamera 1 in Himachal Pradesh, and Kurichi in Bhutan. He was selected by the Government of India and Bhutan in 1996 to start 1020 megawatt Tala hydroelectric project Bhutan. After successful completion of Tala, he was entrusted with 1200 megawatt Punasanchhu 1 followed by 1020 megawatt Punasanchhu 2 project. He was honored with Truk Thukse, the highest civilian award of Royal Government of Bhutan in 2012. After working as managing director at the 3 mega project of Bhutan for more than 20 years, he superannuated in 2018. In recognition of his contribution in Bhutan, the Government of India honored him with the prestigious Pravasi Bharatiya Samman Award in January 2019. Presently, he works as a consultant and is chairman of a panel of experts for Himachal project. Now I request Khazanchi Sahab to please come with the presentation. Khazanchi Sahab.
The topic for today's talk, as you know, is tunneling in Himalayas, technological intervention in Tala project, Bhutan. Now, do we call it technological intervention, or maybe we extend it to some innovation, some of-the-box application of ideas? I will start with the Himalayas, not going to the tunnel first, but reaching a tunnel site. For reaching a tunnel site, it becomes extremely difficult because, as all of us know, hydropower projects are in remote places, in very narrow gorges, and especially if you see Bhutan, very densely forested. And then from existing road network also wasn't that strong there. It still continues to be poor, except for the main accesses provided by Border Roads Organization of India. And from one of those roads, existing roads, the powerhouse site was something like 35 kilometers away. And elevation falling from something like 2,000 meters to 500 odd meters. 1.5 kilometers vertically down. And not only that, en route, even aligning the road itself became a very big problem because of, again, the excesses, the difficult terrain. And the worst one, when we started, we could reach formation cutting to a point which was about 18 kilometers from the 0 point, from the main existing highway. And after 18 kilometers, next 4 kilometers were treacherous. And the project road was in zigs. And at one of the points, if you see the right-hand end of this very first slide, it is connected with that road, which was already existing there by about a year of our having started it. And suddenly came June June 2000, it was 20th and 21st of June 2000, when we had almost 900 millimeters of rainfall, 3 feet of rainfall in just 2 days, 48 hours. So the whole thing slided. If you see the upstream and right-hand side, that is the upstream end of that road that was gone. If you come down to the next, which is not seen here, at that very level, that was the main alignment, even that subsided. So nothing was left. But still we wanted to induct the equipment. So some idea came that we go down through zigs, covering a distance of almost 1.5 kilometers, precisely 1560 meters, 1560, to cover the original alignment of 4.5 kilometers. That means from a grade of say 1 to 30, it becomes 1 in 15 becomes 1 in 5. So these zigs which you see are 1 in 5 grade zigs. And believe it, we could induct heavy earth-moving machinery on these zigs. And gain almost, we had come to start the road construction from the powerhouse end, which is beyond what you see here. That place we had approached through a village which was quite downstream, almost 15 kilometers away, and taken equipment from there, come up along the river bank to reach the tail rest tunnel location. And from there we rushed to reach the powerhouse, and from that end we had started the road. So this zig was to be connected to that road, and we could induct the equipment. By May 2001, this whole exercise was done and we had the equipment outside. And first time, that was the time when we had actually real good experts to visit it for the first time. Earlier in 1998, we had our colleagues from Central Water Commission, our colleagues from GSI, our colleagues from Central Soil and Materials Research Station, and my own colleagues from NHPC, headed by Mr. Brajendra Sharma. And incidentally, on my right sitting here is Dr. Gopal Dhawan. He was also in that team. That time he was very young and energetic. And we had late Gangu Padhyay with us. And they had to come all the way, all this distance on foot, from 2000 meters altitude to 500 meters altitude. Now, if you see the next slide, is a ropeway. So this zig became very, very popular there in Bhutan. Any visitor coming us, any expert visiting us, any contractor visiting would use this. And ultimately it was a boon even in the operational maintenance stage after 2007, when we had a lot of problems, landslides, cloudbursts. This damn thing stayed. Everything else was damaged, but this stayed. That was a big thing. And next you can see the small ropeway. This we did to have at least some manpower inducted. And maybe even after completion of a shift, they start coming back, especially the key ones. Those technicians who get involved in drilling, logging, everything, they would be using this ropeway. So that is the first Himalayan technological intervention for starting a project. In the next, this I have shown that capacity is 1020 megawatts of this Tala project. It's the largest operating power station they have, and it's second largest after Napta Jagdi of Himachal Pradesh, SGMNL's 1500 megawatts. On the right, you can see a beautiful structure. In Bhutan, they don't follow what we say here in India or any other country, a planned development. We have a planning commission, now the Niti Aayog. They don't have a planning commission. They have a GNH commission, Gross National Happiness. They don't put this stress on GDP, GNP. No, it is GNH, Gross National Happiness. And according to them, they're thinking national happiness, it depends on 4 very strong pillars. The very first strong pillar is their own culture and religion. That is the faith, which I am depicting here. Next is the sustainable and lasting equitable distribution of development throughout the country with all the communities, all the villages, urban areas getting benefited. Third is the environment protection. And fourth is naturally the health and the hygiene. On this, if you see in any society, if these four factors are taken care, people are happy. Compared to where we have a lot of affluence, we have a lot of prosperity, but people still taking sleeping pills and committing suicides. This is their thinking and they are following it. So I thought I should be sharing this with you. This was done as soon as the prosperity came from their project. We continued to be operating that project for 3 years after completion. And this is what we did for them that time, right outside the powerhouse. So it's a guardian of prosperity and peace for them. Now, as all of you know, Bhutan location, we know it's in the Himalayas. And if you see, we have in the north, continuous, that used to be Tibet, taken over by China. And it has continuous border with them in the north. And then on the west, we have Sikkim. As we come down to the south, it has first the West Bengal, then Assam. Then you go a little up to cover its east, it'll be the Arunachal Pradesh. And we talk about its area. I have not confirmed this, 38,490 square kilometers of area. It used to be higher. Maybe they have done more surveys and modified it. And its border with China is long, 475 kilometers. Border with us is only 660 kilometers. Altitude varies from 7,500 meters in the north, that is touching Tibet, and then coming down to south, meeting our plains at below 100 meters. It's, in fact, 97 is the lowest. Forest area unbelievable and thick forest, 70%. Annual precipitation varying from 1500 millimeters to 5000 millimeters. I have shown the 5 main river basins of the country. Number 1, you can see, if you see the extreme left, that is in their west. Number 1 is Omechu. Number 2 is Punasanchhu, where this project is located, Tala. Number 3 is Punasanchhu. Number 4 is Mangdechu. Number 5 is Drangmechu. And then the capacity of various projects, I'll be talking to you. First, I will tell you the entire hydropower development estimated is about 30,000. This is excluding, perhaps they may be interested in then pump storages. This is excluding pump storages. Identified schemes as we have presently is 24,260 megawatts. And developed now, even after this Mangdechu's commissioning in 2019, it has come to 2,200 megawatts. Potential-wise, the basin-wise, the first one is Omechu, that is the westernmost. It has a potential of 2,060 and nothing is developed. Wangchu has 2,747 megawatts, and there we have the 336 megawatts Kurchu, Chukha, and 1,020 megawatts Tala. Then in Punasanchhu basin, they have only one small station done by Austrians, that is Bosachu, 64 megawatts, whereas the capacity, the potential is something like 6,600 megawatts. Then comes Mangdechu basin, which has something like 3,900 megawatts, and the first project in that basin was commissioned in 2019, that is 720 megawatts Mangdechu project. Then Drangmechu is the easternmost. It has the highest 8,692 megawatts potential, and only one project done by NHPC there. That is Chukha. No, sorry, this is now Kurchu project, 60 megawatts. All other small ones, if you add up, they become 280 in the potential. And that's all we have there in the country till date. Now the terrain, as all of us know, what is shown here in the shaded white is all the glaciers up, and you'll find hardly any flat land, very scarce. River flowing in deep gorges along steep gradients of 1 in 22, 1 in 25 at all potential sites of hydropower. Number third is the river banks steep, followed by flatter slopes, and this is very interesting about that country. Deep rivers, almost vertical slopes for some height, appreciable heights, and thereafter both banks becoming a little flatter, but again very thick, dense forests and lot of overburden also. Perennial flow of the rivers now and these steep gradients, they offer interesting and tempting sites for hydropower development. And interestingly, except for the dam, all other major structures, there's a minor structure, a small potted yard for evacuation of power. Otherwise, the only surface structure you can see is a dam. This, I have interestingly picked up this geological map. This was updated by them in 2014. If you can see this coming closer to the south in the country, you can see it is written also in the right MCT, main central thrust of Himalayas. And this project, if you see, you have aligned in the second basin, that is Wangshu Basin. This project is slightly away from the border and it falls right MCT, main and central thrust on this project. And if you see this wide blue, that is the river. On the left is north. It is flowing north to south, and here it's from our left to right. And you can see a red spot I have put in the blue, that is the dam. After that, we have complete underground blue lines going to the powerhouse complex is also underground, which is a little darker here. Then a tailor stone meeting the river again. Components would be naturally the concrete dam, as I showed you. 92 meters is the height and 130 meters is the length of the crust. River diversion tunnel is 6.8 meter diameter and 356 meters length. Why I have introduced this here to show you is, even for doing the dam, the first thing is to do a tunnel for its diversion, temporary diversion for construction. And if you see, this is the intake of the diversion tunnel, that is the approach channel from the river, a beautiful site, which originally, where you see this structure standing, this was covered by overburden. And you could make out that this would be that interesting a location where you enter straight into the mountain with lot of cover on your left and lot of naturally the mountain on the right, cover on the right. But unfortunately, as you proceed towards this 350, 356 is the length, under 350, 8-10 meters short of that, it became very difficult to have an alignment which could improve our cover towards the valley, that's the river side. No, it was not possible. Ultimately, it was decided, okay, it's a temporary structure, it doesn't matter. But I tell you honestly, it was a nightmare when we had already started in a big way dam construction, and we could see there was a lot of overburden and some trash they put downstream of the main dam body, and through that we could see the seepage. And unfortunately, but luckily for us, it survived. Otherwise, it would have collapsed, and the diversion tunnel would have been coming into the dam pit. So that's what I wanted to tell you, that the first, if you see the problem in Tala tunneling was here. Next, you can see the descending chambers. We have had 3 descent chambers, 250 meters long and 14 meters wide, 13.5 meters, 9 meters wide and 8.5 meters depth. In these first, second and third, first to get connected to the headrest tunnel, then the second and the third. The third one on its left wall, what you see here on the left wall, almost midway at 125 meters. This wall, left wall, collapsed. Right, it came right up to above this springing of this arch and a part of this also. That was the second, very difficult, lot of efforts to restore it and then redo it. You see the finished beautiful tunnel, 6.8 meter diameter and 23 kilometers long. Once completed, it looks so good. But when you see the details, one gets really goosebumps. Two steel-lined inclined pressure shafts, it has 4 meters, 1.1 kilometer long each. Now you can see here also on the right, I have shown you a picture here, which is actually a collapse in the pressure shafts. And inclined pressure shaft, there's a collapse, and you never know whether it will continue or not. It only comes some muck, you find some stones rolling, and it took almost 6 months, more than 6 months, to be waiting for anything to roll down. We couldn't help. But finally, a decision was taken. It came up with the rails from the bottom. Quite risky to start with, but then people got the confidence and we continued. It has a restricted orifice type surcharge, 12 meters diameter in the bottom and above the orifice, 15 meters diameter, 184 meters long. Again, this became very difficult. And I have shown you a picture which shows only a pilot in this advancing. Machine hall also you can see beautiful, a small car looks a small thing, whole length of it. But this was the second most difficult for handling these geological problems, which I'm not discussing today, but I have listed here. This is also the second. Then comes a D-shaped tailless tunnel, which is 3.1 kilometers long, 7.6, as if it was not enough to be doing 23 kilometers headrest tunnel, and then inclined shafts of again 2.5 kilometers, and then you have these huge big transformer hall and the machine hall, and then you still need a tailless tunnel, and that too that long, 3.1 kilometers. I have shown you both here. This GIS, you see, it is in the first floor, and the ground floor of the cavern is the transformers. Luckily, this transformer hall did not face much of the difficulty, but power was miserable. Now, our own question is an underground development along a thickly forested bank of the river, extending over about 30 kilometers of its length, couldn't have proceeded without a big major of surprises and problems. Can anyone imagine such magnitude of underground construction of tunnels, huge chambers, and long vertical and inclined shafts in young Himalayas getting executed and completed successfully without serious problems and difficulties? No, nobody will agree. I'm certain it will be a big no for all of you. Today, I have already started, but now I will go to the toughest problem in underground construction as we faced in execution of underground components of the Tala hydraulic project. And then the technological interventions and innovative approach adopted to ensure successful completion of this mega project. I have had the I have had the privilege of getting associated with the project as the chief executive. I was a general manager at that time when I started it, and after 2 years, that post was upgraded to managing director of Tala Hydraulic Project Authority, which was then dissolved after 2 years of completion of the project. It was a joint venture project of Government of India and RJB, and I was there right from inception to completion. And thus will be acknowledging this is the place, after telling you that I stayed there from inception to completion. There will be no better person than me to be remembering the contribution of a long list of real experts of our country. I'll tell you that is the biggest satisfaction I have. To start with, we had an option, an agreement signed between the two governments that whatever is not available in the two countries, Bhutan and India, any input for the project, whether it's manpower, expertise, construction equipment, any other equipment, and even the contractors. Bhutan, as we know, especially that time, they had nothing. In the 90s, late 90s, they had nothing. So it was basically to say that Indian resources will be used in food. And then there was a provision that third country experts and also the equipment could be involved, could be deployed if they need be. So once I started, the first thing was to read that agreement. And from that agreement, what I thought was, luckily for us in NHPC, after my coming to NHPC on deputation, between 83 and 97, I stayed in NHPC, 96 end. 83 to 89, I was in Tala. And that was the time when we were trying to come out from the ill reputation of delaying hydroelectric projects in the country and starting new. And I recall the best project done during my time there was Chimera Stage 1, 86, 94. Beautiful project done. But there also since we had to get the finances, also the tie-up was that Canadians would be supporting it. And I tell you, I was told by, in fact, one of the senior executives from NPCC, that time they were in good condition, who later became their same day also. A young boy, his son's age, had criticized Indian working on tunnels. That was in my mind that if we have a tie-up with some foreigner, naturally it will not be the expert all the time. It will be somebody down the line, a fresh engineer, maybe very bright also, but we would certainly not lacking with the manpower of that caliber in our own country. No way. So we thought, what should be done? Our consultants used to be WAPCOs, and in association with, they had associated themselves with Central Water Commission, Central Exchange Authority, Central Soil and Material Research Station. We had the Central Water and Power Research Station, Kadapasla. We had the NIRAN, National Institute of Rock Mechanics, Karnataka. Tie-up was with all of them, and all those experts were available with us. So getting foreigners, especially when the finances are our own, Government of India was financing it. So we sat, Mr. Ramechandra used to be chairman of Central Water Commission that time. Mr. Beg used to be the chairman of CA, and Mr. Partha Sarthi used to be the CMD of NARCOS. I sat with them, and I was almost new to all the three of them. But somehow we could influence each other that ideal would be the Indian expertise only. Because in NHPC, we had seen after Chimera, we did Udi, we did Dulhasti, and for that also we had tie-up where our own people, especially middle order, these experts and the professionals, they got the transfer of technology advantage by going sting in those organizations and also on this project. So we had, and while people would go from NHPC and on the money of naturally NHPC, but we had always associated Central Water Commission and Central Exchange. So both these Government of India organizations were confident. They said, yes, our all middle order coming towards the top, they are all thoroughly now exposed to such culture of working to do good hydroelectric projects. And it clicked and everybody agreed to it. And in the very first meeting, after my joining, that was the third of the authority, in that meeting, it was held here in Delhi, we said that we will not need any manpower from outside India. But yes, technological transfer means the equipment, or maybe some people, some engineers, maintenance engineers, operating engineers, maybe at times. That's what they agreed, and everybody agreed there. But to my surprise, can you believe, Mr. Beg was to retire, he was the first to retire. Before it could go down, to the organization, to everybody who would be getting involved, he got retired. Come to Central Water Commission, slightly we were lucky because from day one Central Water Commission had to be involved. And so the people who continued, they knew, yes, we are going to do it, we don't need any foreigners. And Mr. Ramesh Chandra Bhatt, he retired. I'm telling you, within months. And then left was Mr. Parthasarthi, who perhaps in another 2-3 months, he also retired. So in my age group, all the three had gone. So you can understand now the moral responsibility was remaining only mine. And I take this occasion, I tell you, to thank all of them who worked tirelessly to see that it's I tell you, a model project. If you see the implementation, model implementation model. Now we see the plan and the L section of this headrest tunnel. It will be interesting to have a look at the geology as expected. And based on the detailed survey and investigation carried out for the DPR and also later on for the pre-construction stages, a perusal of the L section will show you, if you see, I have marked in red. Tyomochu is visible at the top. Oh, no, this is Taktichu, sorry. Taktichu at the top. This is Taktichu. And those who have visited Bhutan and driven from Phuntsling to Thimphu by road, they would have stopped at Takti canteen of border roads. There's a deep cut, it's a fault across the river and a perennial flow, small tributary flowing all the time. And that was one area where we had expected a lot of problems to negotiate under that Taktichu, and then downstream, as you see the red line. Next you come to, you will find Padechu. After Tyomochu, that's the location where we had one edit, and around that edit, right in the edit and upstream of that, we had problems. Then if you come downstream further, we have Gedishu, and then we come to Mirchengchu. Mirchengchu, where the red again starts. It goes right up to Sarshap, the full red thing. And if you see the geological section, in the L section, naturally in Taktichu, you will find vertical cover less. In Padechu also vertical cover less. In Geduchu, vertical cover is less, but the advantage was the overburden was small. And the rest of it was solid rock. But again, then Mirchengchu down, right up to Sarshap, was all right if you see the thickness, about maybe 200, 250 meters, the vertical this cover. But unfortunately, something like 170 meters, a drill hole gave the results of overburden. And it had a lot of vegetation, in fact, a lot of paddy fields on the top. At about 1600 altitude, 1700 altitude along the slope. Lot of irrigation and paddy fields. The most treacherous last stretch of 7.2 kilometers between Mirchengchu and Sarshap was geologically the worst. In the DPR, this reach was identified to face the most difficult geology due to a combination of deep overburden, low rock cover, deep cross drainages, and absence of rock exposures. A borehole drilled at the DPR stage had shown an overburden of 70 meters, which later came to be much more than what it was. A thorough review of the DPR stage geological findings was taken up at the pre-construction stage. DPR stage, one can think of a place 30 kilometers of the river reach, where the dam site is almost 700 meters below the existing road, and the powerhouse is 1.5 kilometers below the road, and in terms of elevation. So one can expect to its Sarshap 7.2 kilometers length. So now handling the each phase more than 3.5 kilometers, we thought maybe it would be a little difficult and could perhaps interfere with the surcharge construction also. So better is have an independent edit and come 1.6 kilometers upstream of surcharge and start a new. The place is Kalikola, and at Kalikola we introduced a new edit and proceeded, and that edit 517 meters long we could do just in 2 months. It was in class 3 and 4. Then tunneling up the HRT upstream of Kalikola was the issue. Going down was only 1560 kilometers meters. So we thought that we should concentrate on this. From that junction of Kalikola to 618 meters, it was more or less dry, moderately jointed, quartz biotite gneiss, quartz biotite schist, and amphibolite and quartz bands. An average progress of 200 meters per month could be achieved in this range. Tunneling continued with this is the toughest one. Tunneling conditions deteriorated beyond RD 618 due to seepage and unfavorably oriented joints, resulting frequent wedge failures. Conditions beyond 638, that is just after 20 meters, worsened when highly shattered and highly weathered folded interbands of quartzite, amphibolite, and biotite schist with thick foliation shears started appearing to continue up to RD 660 and the 32 meters, 22 meters, and beyond. Advancing along the original alignment from 662 upstream was treacherous. Alternate bands of quartzite, amphibolite, and biotite schist with shear zones of 5 to 20 centimeters, dipping 20 to 25 degrees into the face, were encountered, which resulted in frequent collapse of the crown. The rock mass was folded and crushed. I have seen in the Himalayas, if you see whatever may be the rock type, quartzites, amphibolite, biotite, it does not really matter. What matters is the close jointing and also the crushing. If you find a crushing zone, gone. And that happens when you meet folds and maybe an occasional fault also. And also within these, there could be more number of joint sets. When it becomes more than 3 to 4, then certainly wedge formations are there. Although very poor geology resulted in large ore breaks, still it was possible to advance in smaller pools of around 1 to 1.5 meters, mainly where the water seepage was managed. However, in flowing situations, the face had to be plugged and consolidated with cement grouting and other measures like bamboo reinforcement. Bamboo sticks and then you force them deep, all native method of doing things. Progress in such literature was extremely slow. You can see what had been done. Lot of drainage pipes put, lot of bamboo sticks forced into this, and at the top naturally the forepoling. At RD 698, a 9 to 12 meter thick cross shear, now imagine 9 to 12 meter thick, with about 2 meter thick clay gouge and about 5 meter thick pulverized quartzite was encountered at the face. At that stage, the rock mass started flowing. The face was plugged again with mud-filled gunny bags. Efforts were made to inject polyurethane grout 2 meters above the ground. It did provide some relief as the seepage reduced in the ground, but it did not improve the stand-up time for providing the positive speed supports. It wasn't possible to proceed even in small segments. We even tried an umbrella of Austrian make My anchors, self-driving ones, 51 millimeter diameter, 12 to 16 meter length, spaced very closely at 30 centimeters center to center. There was also attempted to create a shield under which steel rib supports could be placed one by one. Along with My anchors, deep drainage pipes with 20 meters length were also inserted into the face. A 60 horsepower vacuumatic pump was developed deployed to suck such water from the face, but it would yield a drainage of at best 30 liters per minute. even with a suction pump of 60 horsepower capacity. Bamboo stakes were forced into the face for consolidation. However, the face started flowing. Once the gunny bag, you start removing in part, you attempt it, and it starts flowing. A small section of 1.8 by 2.1, you can see on the right there's a drift. Face is held with great difficulty, and then patching it moved me, then the collapse again. So we got into a small drift, 1.8 by 2.1. It was started to proceed in multiple drifting then. We thought we would do it. The very first process didn't succeed, and finally the entire face collapsed. Now you can see the collapsed face, tragic. Now, after struggling from the junction up to 709 meters upstream, the face collapses, okay, would be all right. No, this mass started flowing and it filled 70 meters of the tunnel, already constructed tunnel. 70, not a small thing. You can see an excavation of almost 7.5, 8 meters in diameter, and the whole thing got filled. Something like 3,500 cubic meters of mass. It had taken 22 long months to tunnel through the difficult strata from 618 to 709 before the face collapsed. Conditions had gone worst in last between 7 and 6 due to a fault in 3 meters. And then as we tried to advance, no. An uncontrolled mass of more than 3,500 meters came flowing to fill 70 meters of wall reconstruction. And it took just 2.5 hours, which, yes, we were lucky. All the mobile things, all equipment which could be shifted out was shifted out. But all the electrical connections, air pipes, everything got buried. At that stage, a very thorough review was taken by a group of experts from Central Water Commission, GSI, WAPCO, THPA. After thorough deliberations over a number of days and site visits, it was decided to abandon 133. 70 was already filled, so we withdrew another 33 meters of the already constructed tunnel and realigned the HRT to reduce the severity of the geological conditions by going deeper into it. See, geology would not change because you are going in the same direction. But we thought, okay, we go a little inside, and we shifted by, center line was shifted by something like 108 meters. We shifted it more into the hill. You can see this is the bypass. On the top right, we have taken the flowing arrow, shows the flowing this HRT coming from upstream, downstream, and where we see the junction, there's a bypass taking a 45 degrees turn, and about 152 meters was the limb length. It would mean for 100 it would mean about 141, but this is more than 100, 107 or 108 meters. So this became 152. Then there's a straight line. If you see the straight reach, 801 meters, and then there's an angle, smaller angle of 28 degrees, and we go right to meet the original alignment. And against a length of 1110 along the original, this realignment cost us 72 meters more, became 1182. A proposal to continue with the construction of a single tunnel for some length. The decision was continue for some length, followed by bifurcating it into 2 smaller tunnels, which could be dealt with lesser difficulty to negotiate the entire length. But we proceeded, and as I use this word very oftenly, luckily or unfortunately, so luckily we could proceed with 1 full section throughout. At the same time, it was decided to induct a regular 4-poling rig to drive. This was all makeshift arrangements. Now a regular 4-poling rig to drive perforated pipes to form an umbrella, and routing through these pipes would create solid arches for minimum 8 to 12 meters length, and later on it became even longer, up to 15 meters. At a time for tunneling underneath. Then there were actually 2 makes. We got 2 machines. Casigundo make 4-poling was imported and inducted for the adverse geological reach. Construction of only 1 full section tunnel was continued to cross the entire shear in specific length of 370 meters. I recall Salal Tailways Tunnel is 2.5 kilometers long. It had at one location something like almost in the middle, 500 meters. With some good bands in between, but otherwise 500 meters. Here we had continuous 370 meters. The Salal Tailways Tunnel also I recall that was treacherous, but we didn't have the equipments like this that time. So immediately what we thought was, okay, get this pipe and perforate it all to be imported. And then drive it in an incline, up incline of about 8 degrees slope with the horizontal and all along the periphery, as you can see, these blue lines. And the varying in diameter from maybe about 45 meters, 45 centimeters height more and about 30 centimeters the span more. And then you start grouting. For negotiating the shear zone, each reach while advancing along the realigned route, forepoling was done along the tunnel perimeter with an inclination of about 7 degrees up radially. A physical model was developed for better appreciation of all concerned because there were people to work. After tunneling under the arch for about 2/3 of its length, say if you do 12-meter long arch, first 8 meters you excavate, support properly, positive supports, and then you introduce the next. That's why the diameter keeps on varying and it becomes more. After you cover the first pull, first stretch, then you again come under it and do this, repeat the same process. The process was repeated in cycles to cover 370 meters of HRT in the adverse geology. This was that machine, and this is how it works. The rig deployed for the ODEX tube drilling system, now is the process, how it is done. Permitted simultaneous drilling and casing of horizontal, sub-horizontal holes in all kinds of poor quality rocks. A pilot bit together with an eccentric reamer drills a hole slightly larger than the external diameter of the perforated pipe of that 140 millimeter diameter. The casing was driven down the hole without any rotation. It just gets pressed. There is a collar, and on that it moves, it goes down into the hole. After insertion of the full casing, the machine is rotated in the opposite direction for the reamer to turn, enabling the bit assembly to then get reduced. It gets basically detached and it gets loose, and on turning you can retract it. The rig performed dry drilling and utilized, again, yes, most important would be naturally, it's not wet drilling as we have all the time. This is absolute dry drilling so that it doesn't aggravate the situation further. And it utilizes the exhaust air to carry cuttings to surface through the shank adapter. A water jet at the time, otherwise at the exhaust there would be tremendous pollution, air pollution. So a continuous water jet is put on the exhaust so that the dust doesn't come up. This is a typical 4-pole umbrella. You can see it something like 30 centimeter centers all along an arc, and this is over now. Forward and under, and then we proceed. In order to reduce the detrimental influence of highly water charged extra drilling holes in lengths 4 meters, 27 meters, and diameters varying from 76 millimeters to 140 millimeters, were provided while negotiating this track. After installation of drainage system, phase stabilization was done by wire mesh and shortcut. It was followed by high pressure cement grouting. These pipes are grouted at 35 to 40 kg per square centimeter to create an arch. In stages of 1 meter length, perforatable, these pipes are provided at 20 to 30 centimeters center. You can see 3 successive here. Tunnel advance reach grouted 4-pole umbrella was carried out in variable diameter extrusion and also supported by ISGM 250 that was specified at 0.5 meters to 1 meter center spacing, varying in diameter for 30 centimeters in radius and 45 centimeters in height. This arrangement was repeated in all successive 4-poling blocks to cover the entire 370. I will tell you, most encouraging and motivating would be the visits of 4th king of Bhutan, who used to be the king that time. And I have written here, Bhutan King's visits used to be motivating. Of course, then when things become very difficult, you sit together for prayers. And here you can see me, a Hindu. In the center is one Mr. Phunsu Norbu, he's a Buddhist. On the left, I don't remember the name, but he's a Muslim gentleman. And finally, the project was dedicated to the people of both India and Bhutan. By that time, the ex-prime ministers of India and Bhutan. That was on 17th of May 2008. Having started the project implementation in early 1999 from a scratch, Tala Hydropower project was commissioned successfully in 2006. And then on 17th May 2008, it was dedicated to the people after running successfully almost for 2.5 years that time. And thank you. I have come to the end of what I had to speak, and now Dr. Dhawan Saab was reminding me that our time is up. And I am prepared in case some questions are to be asked. I'll be there, and mostly some questions like management type. You ask me what was the horsepower of the machine, what was the pressure there, what was the, that would be difficult offhand. But otherwise, all management issues you can be asking, and I'll be able to tell you.
Sir, big thank you to you from DDAG and its viewers. Really, it is like listening story of Tala, which was a gigantic project and a very difficult project because I had been to this site. So anyway, now I think I will invite one by one if there are any questions. And I have received one question from Mr. Dinesh Sati. Sati sir, aap hain? Mr. Dinesh Sati?
Sati is also just from Uttarakhand.
Dinesh ji, are you there? Anyway, his question is related to the stress conditions in powerhouse. What was the stress conditions in powerhouse, sir?
Oh, no, I'll have to refer to all my records.
But luckily, Mr. Rajbal
He did it. He did it.
I can answer.
Rajbal ji, सवाल का जवाब आप बढ़िया दे सकते हैं?
सवाल नहीं,
Yes,
सवाल
yes.
ही समझा मैं.
Khazanchi साहब को नमस्कार, Gopal Dhawan ji नमस्कार. That was an excellent presentation, and I think for last 1 hour I was working at Tala project with Khazanchi saab, as we used to work. And regarding this answer of stress, I think it was around 11 MPa vertical stress, and minimum horizontal stress was 10 MPa, and maximum horizontal stress was 15 MPa, I think, which created much more problem inside the powerhouse. It was very, very, very high stresses with an overburden of about 400 plus meters.
Awesome.
Thank you very much. I think that is the question.
Thank
That
you.
is the answer.
Thank you.
15.
Thank you, Dr. Rajbal Singh.
Okay.
Mr. Dinesh Sati, are you satisfied with the answer? Or you want to say something? Because you are there, I can see your name.
Is he here?
Yes, he is attending. Anybody else? If anyone wants to ask any question, please shoot your question, raise your hand, or write your question in the chat box.
Mr. Rajbal's hand is up.
Just all right.
Sir, may I skip? May I speak?
Yes.
Okay. Thank you very much, Khazanchi sir. It was an excellent presentation as usual, and I think I delivered a lecture on 13th DDGA open house, and where also I also talked about this tunneling conditions with instrumentation and quality control additionally. But the way you were talking today, I think your memory, it really took me back to the working at Tala project, and we enjoyed the working. And particularly at this site, I think I told you during my lecture also, it was main decision making by the management at this project site. We had this failure of the tunnel, and next morning, Khazanchi Saab was there along with our team, and Mr. D.P. Goyal was sitting at counseling, and there only he took a decision that God has given us the opportunity now to divert this tunnel, and this and he told us that let us call it a exploratory tunnel till we get a decision from the government of India and government of Bhutan. And he took a final decision, and next day blast was taken for this diverted alignment. So this kind of decision making was at this project, and that's how we could proceed with an excellent team led by Khazanchi Saab. Thank you very much, sir. It was
thank you, Dr. Rajbal Singh. Now I request Joshi Saab to say a few words, please.
Thank you very much, Khazanchi Saab and Dhawan Saab, for giving this opportunity to me. Whenever I see Khazanchi Saab, I go back to my old times, and I revere him as my guru. So it was really a pleasure and very enriching experience for me to listen to his voice technically on an aspect which is very close to his heart, that is hydropower. And what I wanted to say, I think Dr. Rajbal Singh has already touched that particular part, because in Tala tunnel, and we also used to follow the developments there, the best part of the tunnel was the decision making. And we took a cue actually from you, sir, when we read your paper written by Mr. Goyal and Mr. Rajbal Singh and yourself. And being in NHPC and always bombarded by the question of Himalayan geology in various kind of PIB meetings, why the cost of the project shoots and why are you not able to do anything about the geology. I saw a really bright hope of light here, because this decision which you had taken to infuse a new kind of machine at a time when you were stuck, and you didn't keep on waiting and experimenting any new thing, but the technological intervention, as I call it, was the infusion of Casagrande and the Puntal machines. Despite after having tried, the shifting in alignment and PU grouting, which are the normal means, SOS means which come to somebody's mind. But I think decision making at that time and deciding that we change the technology, we use the big available technology and import it from outside. That was really the crux of the matter. And in one of the PIB meetings later on, I said about this, that if you give a flexibility to the hydropower engineers to infuse such technological interventions at an appropriate time, not worrying about what was provided in the DPR, because the DPR says the engineering which we do is certainly, I would not say deficient, but it's just lacking because there's an inherent limitation of the investigations actually, which you really cannot foresee. So having said that, this flexibility certainly must be allowed to the engineers, and due to the dint of our governmental system which we have, we are not able to actually do a similar thing here in India. So I took this opportunity to do something like that in Magnachoo. So in Magnachoo, even though geology was supportive, but we did provide all kinds of dress technology and pipe proofing, etc., right in the beginning itself. Even though we were not able to satisfy the Central Water Commission and the CEA at that time, because they say when geologists are saying that your rock is good, why you should be needing all this kind of technology. But we said, no, we do not know. On one hand, we are always talking about the treachery of the geology. We do not know when you are going to have a water ingress and a shear zone. So I think it's better to be prepared beforehand. If you do not get into any kind of problem, it's okay. So Tala tunnel, for that matter, showed actually the way the entire hydropower industry. That's my concerted belief. And I thank you very much for that. You have been always so modest actually in your achievements. But I would say this was the one which is an epoch-making kind of change which you have brought into the hydropower industry, and we will ever remain thankful to you. So thank you so much, sir, once again.
So thank you, Joshi sir. We are really lucky that we have this opportunity today that Mr. Khazanchi is with us, and I'm luckily sitting just beside him because he has given so many projects to Indian hydropower industry. His entire life was dedicated for development of hydropower in this part of the world. And Tala was certainly one of the best gifts he has given, and one of the most challenging projects which he has commissioned. And we are highly indebted to him.
Credit goes to the man who is there. A young man joining and starting in a big way and did excellent. And I recall he met an accident.
Joshi?
Yeah.
Achha.
And then on his return, he had some phobia of not going for construction.
Okay.
So he stayed back and doing all real burden work while he was doing. One day I requested Mr. B.B. Mukherjee, was his immediate boss. I told him, you send it, I would be not the one going to site at 8 in the morning. I had my own rules. So I told him in the morning, if he's in the office, you should send him to my office, send a word to him. So next morning he comes. But I said, we have something important at site. I still remember we drove down to the site and I stopped somewhere and he also got down. He got down, we were doing something and I suddenly got into my car and went deeper. Because he was left behind. After some time, after 10-15 minutes, Mr. B.B. Mukherjee comes to me. He says, sir, Mukherjee Saab comes to me and what has he to do? You have got him here. I said nothing, whatever he was doing before that unfortunate accident. That's all. I still recall.
Yes, sir. Anyway,
but that was the dedication here, actually. Very bad fracture.
These stories are so interesting that we can listen to you for hours together. But unfortunately, we have a norm that we will complete our program in 1 hour, and today we have overshot by about 15 minutes.
I have to tell something about Dr. Rajbal Singh.
Okay,
okay. You know all the papers written from 2002 onwards for different aspects of Tala, where he contributed lots. He was the one who then edited the whole thing in 2 compendiums. And that is actually, I don't know whether they have the soft copies now. I have, in fact, the hard copies, 2 volumes. They are there, all. And he worked very hard on that, getting everything, then getting it published, and finally.
So, sir, it is time to close now. जी, आप कहना चाहते हैं डॉक्टर सिंह कुछ?
Sir, thank you very much, Khazanchi sir, for remembering that. And I think a lot of people are using it. And I am still having the soft copies. I keep on distributing it. I can send one to DDAG also, so they can also distribute it. Because that's 992 pages and 103 papers. I think that's a very good volumes actually for hydropower projects. And all this data was compiled because of the motivation from Khazanchi Saab and DP Goyal Saab, and we did a wonderful job under their guidance. Thank you very much, sir.
Thank you. One day we will keep a chat show on this topic, wherein we will invite all stalwarts and we will have, we will listen more and more about the technological interventions and the problems which were done. So now it is over to Mr. Ashu Mathur for some announcement from DDAG side.
Thank you very much, Dhawan sir. I, on behalf of DDAG, thank you all the participants for joining, and especially RN Khazanchi Saab for a wonderful talk and a nice presentation, which had enlightened all of us. As I want to convey that all these videos are being uploaded on our YouTube channel. I request everyone to view it. They can circulate it to their colleagues, and you can also subscribe our channel. So it will be better for its betterment. So this was all about today's talk. So we will meet again in our next open house edition, which will be 25. So thank you very much. Thank you once again.
Thank you.
Thank you, sir. Thank you very much.
Thank you, sir.